So today we will learn something about how can we use direct and indirect proof to prove some conclusion from already known premises. Okay, so basically it's still the same thing. We just need to apply those rules we learned, the rules of inference we learned to something we already known, and we do some deduction there. Finally we reach some step to reach the conclusion. So that's what we want. That's called a direct proof. Okay, so from what we already know, we're doing some deduction to those expressions, and then we finally reach something that is the conclusion. Okay, so that is one way of doing the proof. Another way of doing the proof is called indirect proof. So in order to do indirect proof, we also this is basically still the same. We have a whole bunch of things we already know. However, when we are doing the indirect proof, we assume that the conclusion is wrong. So we assume if the conclusion is light is on, so we will assume the conclusion is negation, light on. Okay, we assume this conclusion is wrong, is false. Then with those premises, we reach some of the at some point we're doing this deduction. We're still doing the deduction with the rules of inference. At some point, we will reach, if those things we are going to prove is correct, at some point we will reach that there's a contradiction there. So whatever we deduct, the expression from our deduction will have some contradiction to the one of the premises. So then we can prove that from that we can prove the conclusion. Okay, so that means if the conclusion is wrong, there is a contradiction in the premises, then we can prove that this conclusion is correct. So two ways of doing this proof. First, let's see the first way. How can we do that? Okay, so example here is the fact that a conclusion valve open follows from the premises normal state, open command, and negation test state. So this is the thing we want to read. We have this premises. The premises is normal state is true, open command is true, negation test state is true. So we have those three premises we already known, and the conclusion is we want to do is the valve open. Okay, and this mark here, basically we will replace it with implication. Then we will see how can we do that, and also we will replace those commas with the and conjunction. Okay, so it represents a question: would the valve be open if the reactor is in its normal state and the open command has been typed and the reactor is not in a test state? So that's basically those three conditions. You can call them conditions, or you can call them premises. So those are the things we know, the truth there, and we want to draw some conclusion from the truth. Okay, so and we can form them as a normal state and open command and negation test state implies valve open, things like that. So but can we do that here? Can we prove this valve open from normal state, open command, and test negation test state?
Yes.
And how can we do that?
If there's no contradiction.
No, let's forget about the contradiction. We want to use the direct proof for now.
Oh, I guess not then.
Right. Because we didn't give any other. The condition says not enough. We don't know the relationship between these things, right? The normal state, the open command, the test state, the valve open, right? We don't know anything there. This is just an example. Let you see that this is premises, this is conclusion. Okay, here, but next thing we can do something there. Show the conclusion follows from the premises. Okay, so closed, open or closed, open. So there is something there, because the open is the conclusion and the premises there. It seems like we should have enough of the premises to have this conclusion. So let's see what is here. Can I make it? Okay, fine. Alright, so we're rewriting it. We rewritten it as this, and what I said, we replace this comma with conjunction, and then we replace this mark with the implication. Okay, so this is the expression here, right? And then this is premises. And at the right side of this implication is the conclusion. Okay, for the first step, what we did is we change this part, the whole thing to the left of implication, to negation, right? To the negation, to this negation, and then or open. So here we explain why can we do this change. It's because we use the rule of implication, right? Let's see what is that rule. If you still remember, this is a very critical part. So this, we have this implies IMPL, okay. So P1 implies P2. We can rewrite it as the negation P1 or P2. Okay, remember this one. This is the most critical rule where we need to use in the direct proof. Okay, so anything, whenever you read this, read the question, you will have somehow some of the question directly give you this thing: closed, open, closed, open, closed. This thing. So you need to rewrite it as the conjunction, and you need to rewrite this conjunction and implication. Then the next step is you need to use the IMPL, this rule, imply this rule to change this implication to or, and you put this negation in front of this whole thing to the left side. Okay, and then the rest steps is to prove this thing the rest is to prove that thing. The first one, expression 1, will deduct to true. Okay, so that's basically the step. So the first step is you trying to use some variables to replace whatever mentioned in your question, and then you rewrite them as this conjunction and implication. The third step, you use IMPL. You use this imply rule to change this implication to or, and then put this negation to the left side of this implication. Okay, then the rest of the step is to prove this whole thing marked as 1. Expression 1 is true. Okay, so you can see we did a lot of things, 2, 3, 4, 5, and 6. Finally, we prove this thing is true. Then we know that the conclusion is true. Okay. So what you need to do here, after you've written to this kind of form, then you kind of put use this. Let's see, what is this rule? If you're still not familiar, we didn't use that. So it's basically you put this negation. You put negation inside. So first we put negation inside. We change this conjunction to disjunction. I mean from 1 to 2, expression 1 to expression 2. Okay, we're clear. And then from expression 2 to expression 3. From expression 2 to 3, we eliminate this negation. We eliminate this negation. And from number 3 to number 4, what we did is we just changed the order, and from number 4 to number 5 is basically we group this closed and open, and then we find that this is closed and open, or negation close or open, right? So this is always true, because basically it's everything there. If this is true, this is gonna be false. If this is true, this is gonna be false. So one of them has to be true. At least one of them has to be true. So this is always true. So that's the basic step of the direct proof. Okay, let me repeat it again. So what you did is, first, this is the thing you want to prove. At the left side, it is the premises. Premises is something like we already know is true. Okay, and we want to prove the open is true. Okay, then whatever we want to do is we rewrite this as so this is true, negation close is true, it's one of the premises. Another premise is open or close is true, it's another premises. So both of them are true. We use the conjunction here, right? Negation closed and open or closed. If both of them are true, if we can imply, if this expression, so left side, can imply that open is true, then we know that from the premises we can have this conclusion. Okay, so logically, is it any problem? Is there any problem to understand this logic? So let me give you a maybe more solid example. Okay. If we have a first premises, we have a first premises is today is February 14th. Okay, and the other premises is we got chocolate. Then the conclusion what we want to prove is we have a happy Valentine's Day. So the thing is, you have to both of them have to be true, right? You have to have chocolate. You can have chocolate in any day, but maybe it's not February the 14th. Okay, so you have to have this chocolate, and then it's 14th. Then we can have this conclusion. Implies February 14th and chocolate implies happy Valentine's Day. Okay, we want to prove happy Valentine's Day through the two premises, February 14th and the chocolate. Alright, so here it's the same. We want to prove open is true through negation closed and second open or closed. Alright, most critical part is this. We change the imply. We change this imply to an or, and then we put a negation in front of. We put a negation in front of the basically all the premises. Okay. So it is a rule, IMPL, imply. Okay, and the rest step is you apply whatever rule you want. Maybe there are different ways, but you apply whatever rule you want to prove the expression 1 will be deducted to true. Then we can prove, okay, this thing is true. Okay. Okay, this is another thing called channel open. So this has three premises: channel open, receiver ready, line closed, and channel open implies negation receiver ready. So, and the conclusion is negation line closed. It seems that we do not have any conditions there to help us, but however, those are the premises: channel open, receiver ready. So actually this logic that actually connect this channel, receiver, and the line is here. Line closed and channel open implies negation receiver ready. So we need to play with these three conditions and this negation line closed. We need to play these three conditions, line closed, then we somehow prove this is true. Okay, so let's try to do this. Channel open, receiver ready. So this is the first. This is the first thing, right? Receiver ready. is the second premises, and line closed and channel open implies okay. So this is the premises. Conclusion is location premises. Okay, so this is the thing we want to do. We want to prove negation line closed. Okay, let's do it step by step. Okay, still remember first thing what we do is first just say the thing you in your mind. Yeah.
You change the commas to and symbols.
Yeah, something like that. So we jump to step. Channel open, right? And we put the and instead of all those commas, right? And what? Yeah, receiver ready, right? And what else? Imply or?
And line close.
And actually, it's better to put this thing here. We copy paste or put this thing into this place. Let's here. Okay, so it's channel open and receiver ready, and this whole thing we group them together. We need to group them together. And line closed and channel open implies receiver ready, right? Then what else?
Use the imply rule.
Exactly. Imply, yeah, we imply this conclusion. Okay, see that? So this is the thing we want to do. Okay. Okay, here it's a little bit different from the last example. Because in the left we actually have another implication there, right? So in the last example, it's simple, just and or implies. But here we have in this premises we already have implies there, right? But it's the same thing. Because this imply also has a value. If you remember those true false table, truth table. Yes. Okay. Okay, so we actually have this channel open. We write them as CO. Yeah, this is a good idea. Channel open. Receiver ready. line closed. Line open. Receiver ready. Line closed. So that we did this. It's the CO and RR LC CO. We don't even need to know what each variables are. We just need something there to do the proof, because the logic is already explicit. Okay, so this is the thing we want to prove, right? We don't need to know what are those. We just need those notations to tell us this logic. Okay, then the second, yeah, it is using the IMPL. See, we have two implies and imply. This is the thing we want to prove. This is only one of the premises, so we need to rewrite that part as well. Right? We don't want to see this imply here, because it makes things not that easy. So what we do is we use that IMPL. Okay. We change the implication to what? For or, right? And then don't forget we need a negation here. Okay, we need negation here. So here we can actually put the negation inside. Let's just put it inside. This becomes or. So it becomes something like this. So we get rid of this imply. So this is what we did here. Negation or negation or negation implies LC. And this is the group. We did this, we change the order, then we associate. Yeah, this is a pretty complex one. Okay, let's see if we can have some quicker ways doing that. Okay. Yeah. Seems pretty complicated, but actually it's not. So this is the yeah. Okay, so number 3 basically it's changing this let me see how this So the idea here is we have this RR and we have this negation RR. So we're trying to put them together so that we can have a true or false. Because if you know RR and negation RR, it becomes
False. Or no, true.
yeah, R and negation RR, because we basically have all these things. Yeah, and but RR or negation RR, what's that gonna be?
Well, that one, well, and would be false. Or would be true.
Yes, or would be true, but and would be false, right? So we're trying to combine those things together. Okay, so we kind of need to anyone has any idea how do we put them together? At least we need to like group them and switch the order, right? So basically we want the RR to go RRLCCO, RR LC, and we can actually group them. So we actually did something to 2. So what we did is a commute, and we did this association. Okay, so I won't specify everything here. It will be time consuming. And then CO, and then we are able to put this RR inside this thing. So yeah, let's get rid of this. So it become RR and negation RR, right? Or actually we can try this. We can group them together. Then we can do this like CO and RR and negation RR. This is one thing, because basically we put this COR together with this negation RR. Okay, and then we put follows this is or and.
It would be the
And so what is the name of the rule? Let's look at here. So what we want to do is we put an and or, right? See this distribution? If we put and into this or, you see that? We actually have this P1 and P2, but we keep this or, right? So here, we want to put this CO and RR into this 3 things. So CO and RR and negation RR. The second thing is CO and RR and negation CO. The third thing is CO and RR and negation LC. So what is in between of the 3 things?
or
Yes. Yes, or, because here this is the or, right? We keep this or. And then it's CORR. CORR and what? Negation CO. Right? Another OR. This is negation LC, yes. So this whole thing, come on, implies, don't forget that, implies negation LC. Okay, now we have a, what is that? Okay, negation LC, right? So what we did here is we did number 3, we applied this association, we applied whole bunch of the commute, we apply a whole bunch of distribution. So we apply a whole bunch of those, we finally reach here. So any problem right now from number 3 to number 4? No problem. No problem. Okay. So we know how to go from number 3 to number 4. Number 3 to number 4 is just basically put this, combine CORR with RR, CORR with CO, CORR with LC, and then put this OR, because this is OR. That's the rule of distribution. Okay. Okay. So far so good. All right. Then number 5. Now we find a whole bunch of interesting things, because we find RR and negation RR. False. Here actually we have a CO and negation CO. False. Yeah. So we have a bunch of false here. So it's CO and a false, right? No problem. Or RR and a false, right? The second group. Then we have this or with those things we do not know yet. Implies LC. Right. Number 6 is we find a false, 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 false. Right. Anything and this false becomes false. Yeah. So it's false. It's false or false. Or this thing. Number 7. So because they are all false, so this whole expression, it depends on the last part, CORLC. CORRLC implies LC, right? Then again we apply that. So this is much easier, right? Much simpler than the first one, because it basically only have something there. So number 8, this is what we want to prove. So we replace this imply with an or, right? So this whole thing becomes copy, paste it. We change this to or. Also, we put a negation in front of it, right? Then we have, if we have some sense, we're trying to eliminate this negation, right? So it becomes negation CO. What should I put? Or and? Or. If you put this negation inside this brackets, you put the negation in front of each of the variable, but you change it from and to or you change from or to and. Okay, so be familiar with that rule. Negation or negation LC, it become LC, right? Or negation LC. So what do we have now? Okay, it's Valentine's Day. So we have CORR LC LV. What have we seen here? Have we seen some hope here? Something fun? Yeah, so that's true. It will be true, of course. But why?
Premise or not premise will be true.
Yes. So this part is actually true. This part is actually true. And we can group them. If we use the association thing, we group them. We have this true here. This is true. Okay. So we have, after that, we have this and this, this and this. We don't care what's that, but that's true here. Okay. Then the whole thing becomes true. Okay. Then we finally prove this thing. Channel open, receiver ready, blah 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 from here. Actually, logically, it's hard to tell if we can get this conclusion from here, right? Because there are too many steps there. But if we use this propositional calculus step by step, we will have those deduction there. So actually, I didn't do this step by step. I do something combined in one step. You can do that as well, as long as you put this here and tell me what rule have you applied. It should be fine. Okay. But if you look at this material in the D2L, it's actually have a pretty detailed step there. So yeah, basically it applies just one thing at a step, so it's more clear, but it's basically very complicated. We don't want things to be that complicated, especially when you are pretty familiar with those rules. Actually, those rules are pretty simple. If you have used it once, you will have that impression there, right? Like you can switch the order, right? You can easily switch the order. You can group. if it's or and, if or is or, you can just freely group them. Or how you put this negation inside is basically you change the and to or, right? Okay, it's a hard part, but yeah, we prove it. Yeah, this is another thing. Example 6. This is a specification, contains the sentences 1, 2, 3. Those 3 sentences. Yeah. So the conclusion is the reactor will be in a non-operational state. So yeah, I won't do it again, but this is basically the same thing. We have three premises, S1, S2, and S3. What we want to prove is the alarm will result in a non-stop. Oh yeah, this is this is a little bit different. So we have those premises. And also we have this something to be true. So alarm, non-stop. So last example, we just proved this non-stop is true. But here what we prove is alarm implies non-stop is true. So basically it's still the same. We just need to treat this alarm like one of the premises. So it basically is S1 and S2 and S3 and this alarm result in this not result, it implies non-stop. Yeah, basically it's here is the alarm and S1. This is and this whole thing is S2 and S3. We proved non-stop. So basically same thing. It's just you need to do is you play around those rules and you combine different things to see if we can actually get a true or get a false from there. Most of the time you just combine a negation like A, negation A. If there's and or, you kind of try to combine them together to see if we can get anything there, right? So it's the same thing. I won't explain them step by step. So at last we prove a true. Yes. Okay, so this is the proof. Let's repeat it again. First we have those premises and we use the and to connect those premises, right? And then we use and after we connect those premises, we have an implies the conclusion we want to prove, right? And then we remove that imply, replace that with an or, and put in front of those premises we put a negation. And then it becomes a propositional calculus, and we play around with a whole bunch of rules to make it deduct to true. Then we can prove it. Okay, so that's direct proof, and we also have an indirect proof here. Let's quickly go through. Basically, it's still pretty similar. Everything, no matter what it is, it's simplify or it's a proof, no matter indirect or direct, just form a expression and then play the expression with all those rules. Try to combine them, try different combination and see if we can actually have those true or false directly come out of that. Most of the time it's you can do like something and true becomes true, something and false becomes false, and something and negation A and negation A, or A or negation A result in true or false, things like those. to simplify. Yeah. Okay, so this is thing we want to demonstrate. Negation channel will result in this sender, and channel open or sender is known from the system specification. Yeah. So what we want to do is this thing. This sender is the conclusion we want to have. Okay, sender is the conclusion, and we treat channel open as one of the premises, and then this channel open or negation channel open. Sorry, negation channel open is one of the premises, treated as one of the premises, and channel open or sender we treat it as another premises. However, here we also assume this conclusion is already known. We assume it's false. Okay, so we assume sender is false. So here, sender is false. We assume sender false. So here, PR1 becomes negation sender, which is true. Okay, so then we have three things we can play with. First is the conclusion. We get something from the conclusion. We assume the conclusion is false. Then we have this negation conclusion is true. And then the second, and this PR2 is one of the premises. It has to be true because it's a premises. PR3 is another premises. It has to be true. Okay. So we do some change here. Let's see, what did they do? Sender or channel open. Okay, so here we know that if channel open is true, negation channel open is true, right? Which means channel open is false. So here, channel open or sender. We know sender is false, so channel open or sender becomes true. Let's see. The sender or channel open becomes, because channel open is false, so sender or channel open becomes this depends on the sender, right? Number 3. So from 1, 2, 3, is that clear? Because channel open is false, so anything all or false, it all depends on that thing, because you cannot count on this false to make the whole thing to be true, right? Sender or false becomes sender. No problem, right? No problem? Seems a lot of questions there. So if it's something or a false, the thing becomes depends on that something. Okay. Okay, so the sender. And then we put this we put this sender and this sender. It's 3 and 1 and 3. Let's see. Putting 3 and PR1 together, we are N5. PR1 sender. Oh yeah. So this is what we have. We have this sender to be true, right? Because we deduct from everything, sender or channel open is true, and sender or false, sender has to be true to make the sender or channel open to be true. Because what we already know is number PR3, channel open or sender is true, right? Channel open or sender is true. Now we know that channel open is false, then sender has to be true. Okay, basically 1, 2, 3 says this. Sender has to be true. So sender, if sender has to be true and negation sender has to be true, that's a contradiction. Okay? this is a pretty simple example. I want to. Okay, so this is. Let me explain it again. Okay, so we have this PR1, PR2, PR3 come from the premises and our assumption to the conclusion. So PR1, PR2, and PR3, all of them have to be true. We assume all of them is true. Okay, no problem, right? Okay, if PR1, PR1, PR2, PR3 is true, from PR2, let's say what is PR2? PR2 means negation channel open is true, right? Which means channel open is false. Okay, if channel open is false, let's look at PR3. PR3 is channel open or sender is true. If channel open is false, here channel open is false. Channel open, so it becomes false or sender, right? False or sender is true because PR1, PR2, PR3, they are all true. So here it becomes channel open becomes false. False or sender is true, which means sender has to be true. If sender is false, then false or false becomes false. It violates this PR3. So false or sender is true becomes sender is true. We know number 3, sender is true, right? It is a direct confliction because sender has to be false in PR1, right? Because negation sender is true, so sender has to be false. So sender becomes sender, and if for all those to be true, it requires we have the deduction that sender and negation sender is true, which is impossible, right? So there is a contradiction there. Okay, so that's how we find this contradiction. All right. So we assume all the premises are true and the conclusion is false. Generally speaking, if this leads to a contradiction, it proves the conclusion can be deduced from the premises. Okay, this is another thing. Same thing here. We have this is what's been given to us. Two premises. Closed implies shutdown. Open or closed. We want to demonstrate open implies normal. Implies this. Actually, this is the conclusion. After this mark, the normal or shutdown is the conclusion. Okay, and this open implies normal. We treat it as another premise. Okay, it's another premise, so that we have those four things here. S1, S2, open implies normal. PR2. And also the negation of the conclusion. So negation, normal, or shutdown. So we have these four things. PR1, PR2, PR3, PR4. We assume all of them are true, okay, from the premises and the conclusion. Conclusion is false. Negation conclusion is true. And then the premises are all true. Then we kind of here from this normal or negation normal and negation shutdown comes from the PR1. We basically put the negation into those brackets, right? Into the brackets, right? When you put negation in, you change and to or to and. Yeah. So yeah, if A and B are true, we can separate them and each true using AND 5, because A and B, if that has to be true, both A and B has to be true, right? So we know normal, and we know negation normal is true, negation shutdown is true. Okay, then we are looking for some contradiction. Okay, from PR2 and 2. Yeah, from PR2, what we see is open implies normal, but now we know negation normal. Negation normal. Okay, so from PR2 is normal implies open implies normal, but now what we know the truth is negation normal, so we know that negation open is true. So that's the rule. That's the rule of this. Let me show you this thing. Implies not. So if we know P1 implies P2 and negation P2, we know negation P1. Okay. Maybe you're not quite familiar with that rule, but it's a rule there, so you have to be familiar with that.
Can you talk about OR 5?
OR 5?
I didn't really understand.
P1 or P2 or 5. We're not using that a lot, but you remember that we do not have that equal sign over there, right? So if P1 is true, we know that P1 or P2 is true. No problem, right? Right? But we cannot do it the other way. P1 or P2 is true. We know nothing about P1 because it could be P2 is true. P1 can be true or false, right? So it's not like two-way thing. So implies not. Okay, let's go back here. We don't have a lot of time. Implies not. We use implies not. We know that negation open. So this is the thing we know. And also we know that negation closed from PR3 and 3. Let's look at PR3 here and 3 shut down. It's the same thing. We use implies not from PR3 and 3. So closed implies shut down. Now we know negation shut down, which means we know negation closed. Okay. And now we know open and negation open and negation closed, right? Because they are all true. Number 5 and number 4. Also, we apply this rule and 5. So and 5 basically it's both conditions becomes and. Yeah. So we know that negation open and negation closed. Then we take this out. We take this negation thing out. Okay. Negation thing out, and then we become from this and to this or. Okay. That's number 7. So we have this. Negation open or closed. Let's look back at PR4. PR4 says open or closed. But however, it's being deduced to negation open or closed. So there is a contradiction. open or closed. The other thing is negation open or closed. So that's a false. It's a contradiction. Okay. So basically, you play around with those rules, transform them to find out, yeah, these things. Negation closed and closed. Negation A and A. So those things make them become true or false. Yeah. Also, these two examples, these are examples that you get somehow you get a true by assigning the by assuming that conclusion is false. So that means you cannot prove it. No contradiction there. Yeah, this is also true. Yeah, no contradiction. So after play a while, you may find, yeah, there's no contradiction. So we cannot just prove it unless we have more conditions or premises or more premises. Okay. All right. So this thing it actually requires a lot of practice for sure. Yeah. The whole idea is pretty simple. You just change the formation. You just transform it, play around with the rules to find if we can find the true or find if we can find the false. It's pretty easy, but you just need to familiar with those rules and how you play with them. As long as you practice more, you have those sense. Okay. So next class. So next week is the midterm. So we will not meet here. You can take the midterm online. It's open note. Okay. You have a whole week to take that midterm exam. Okay.
Which modules are we covering?
Huh?
What are the modules are we covering in that until whatever is taught now?
A week. I think if you look at here.
And you said no class Monday or Wednesday?
Right. You have the whole week to finish this thing. The week 7, you have the whole week to finish the midterm.
So is it timed?
No, it's actually a PDF. You have the whole week to finish it, open note, and it's actually, I want you to practice through this midterm also. So you have the whole week to practice, to finish it, and you submit to this Dropbox. Okay? I will open. Yeah?
Is it available from today?
No, I will make it open on Monday.
Okay.
Yeah. Okay. So practice. Most important thing, practice. I can talk to you like 100 examples, but still you get nothing until you start to practice. Okay. All right. Thank you very much.